Okay, here's part 2, which is looking at what happens to frequency, wavelength and speed when we're looking at refractive index. And so again, that's just the points that are going to be covered. Okay, frequency. So the frequency of a wave is determined by the source that is making that wave. So what that means is it doesn't change. Once the wave has left the source, it will keep that same frequency. Okay, so the frequency stays the same because otherwise it would not be the same wave. But we know that when the wave goes into another material, so for example, going from air into glass, for example, it's going into a more dense material, so it's going to slow down. So if the speed or the velocity of the wave is changing, but the frequency is staying the same, then the wavelength must also change. And that's what we're going to be looking at, how these things are all linked up. So, for example, we've just said that we've got a wave going from air into glass. The frequency in air is the same as the frequency in glass. Now we know that frequency equals speed over wavelength, or v over lambda. So what that means is that the v over lambda for air must equal v over lambda for glass. If we rearrange that, then what we can say is that the ratio of the speeds in air and glass is equal to the ratio of the wavelength between air and glass. So v1 over v2 is equal to lambda 1 over lambda 2. Okay? We can then say that we can then link that to Snell's law and say that n2 over n1 is equal to sine theta over sine theta 1, sine theta 2, which is also equal to v1 over v2, which is also equal to lambda 1 over lambda 2. You're never going to be using all of those at once, but what that means is you can basically pick any pair. So if you know the refractive indices, you can work out the speeds. If you know the angles, you can work out the wavelength, and so on and so on. Okay, so again, we have got the n2 over n1 with the 2 on the top, and the other ones are all with the 1 on the top. So you would then be switching it around, so it would be n if you were looking at the link between them. So here's an example. So if light is travelling from air into glass, and the speed of that light is changing from 3 times 10 to the 8 metres per second to 2 times 10 to the 8 metres per second, and it's asking us to work out the refractive index of the glass. It tells us it's going from air, so we know that n1 is just 1. So we'll look at that big equation, or set of equations that are all linked together, pick out the two that we're looking at. So we're looking at refractive index and we're looking at velocity. So it's just going to be n2 over n1 is equal to v1 over v2. Stick the numbers in. 3 times 10 to the 8 divided by 2 times 10 to the 8 gives us a refractive index of 1.5. Refractive index, remember, doesn't have any units, so it's 1.5. Which makes sense, because if the speed is changing from 2 times 10 to the 8 to 3 times 10 to the 8, it's doing it the other way around, I suppose, then that would be an increase of 1.5. It'd be 1.5 times faster, or 1.5 times slower. So the refractive index is also going to be 1.5 times faster, or bigger or smaller. So another example here. So again, we've got light coming in from air. This time it's going into water, which has a refractive index of 1.33. We know the angle it goes in at, and it's asking us to work out the angle of refraction in the water, but also what wavelength would that light have in the water. Okay, so there's the question again with the answer beside it. So first bit, you're just going to be using Snell's law to work out the angle in the water. You can follow through the work in there. We've got 1.33 as our refractive index. 30 degrees is one angle. We're trying to find out the other angle. Follow that calculation through, and we should get an angle of 22 degrees. Remember, your answers should always be to the same number of decimal places, or the same number of significant figures as is in the question. You can go up or down 1 or 2, but because the angle going in is given to the nearest whole number, I've given the angle in the water, also to the nearest whole number. So I've just kept it consistent. Then it's asking us what the wavelength of the light is in the water. So we're just going to do the lambda 1 over lambda 2 is equal to n2 over n1. That's the easiest way to do it because n1 is 1, but we could have looked at the angles, could have put the angle numbers in instead. So we end up with 650. I've left the nanometers off because we'll just remember to stick them back on again at the end. So 650 over lambda 2 equals 1.33. Rearrange that and we end up with 489 nanometers. Okay. So at this point, pause the video, do questions 3 to 5 on pages 28 and 29. Again, you might have done some of these before, but it won't do you any harm to do them again. Now, this next bit is where it just gets slightly more complicated because what is happening in your medium depends on the light that's coming in. Now, normally in questions that you are asked, they are like the question that we mentioned previously, this one here, for example, where you're talking about laser light. So it will be talking about light of a specific wavelength, okay? So because that light is, we're just talking about one part of the spectrum, one very specific part of the spectrum. But what's actually happening if you put white light in is, you remember that you stick white light into your prism and that light refracts as it goes in, but each part of the light refracts a different amount. So you've actually got lots of light there that's got lots of different frequencies and wavelengths before it hits the prism. So how it behaves when it gets into the prism is going to change slightly depending on the light. So violet light is refracted more than red light. So what that means is that the refractive index of violet light must also be slightly greater than the refractive index of red light. If it's refracted more, it must then have a slightly higher refractive index. So the refractive index is not just to do with the material. It is also affected by the wavelength of the frequency of the light that is coming in, okay? So what that also means is if the refractive index is slightly different from them both, it's going to affect the speed slightly differently. So here's an example. So white light's hitting the prism and it's producing a spectrum. The refractive index for red light in this particular prism is 1.51 and for violet light is 1.53. So the first thing you notice is it's a very, very, very small difference, okay? Which is why we would tend to say that the refractive index of the material is a set number, because although it does vary with the different colours of light, it's a very, very small difference. So what they're asking you to do is to calculate the velocity of each colour of light in the glass and to calculate the angle between the red ray and the violet ray in the prism if theta 1 is 30. So if we look back up there, so that's the angle that it's going in at is 30 degrees. What's the difference between the red and the violet light at the point where it refracts as it enters the prism? So I've just worked out, well, I've just shown the working for one of them, just for red. So I've been lazy this time and I've just written n equals v1 over v2 because we know that the one on the bottom is 1 anyway. So for red light, the refractive index is 1.51. Velocity before it goes in is 3 times 10 to the 8. What's the velocity when it's inside the block? Rearrange that and we get 1.99 times 10 to the 8 metres per second. If we do the same, but change that 1.51 to 1.53, then we get, for the violet, we then get 1.96 times 10 to the 8 metres per second. So again, you can see that the difference in the speed between the two is very, very small, but there is a difference in the speed between the two. Part B was then asking you to work out the angle between the red and the violet ray in that prism. So at that point, we're just looking at comparing the two refractive indices inside the prism and the two angles working out the ratio between the two, doing some rearranging, and we end up with the theta 2 being 29.6 degrees, which means that the difference is only 0.4 degrees, so it's not very much. If you substituted, if you could do 1.99 times 10 to the 8 and 1.96 times 10 to the 8, use the differences between the two velocities and to work out the differences between the two angles, you should just get the same answer. Okay, so you've now to calculate, to complete questions 6 and 7 on page 29 of your booklet. At least one of those is similar to that one that I have just done. Okay, and then when you're ready, carry on the last bit. So the last bit, just going to whiz through this, is just some applications of refraction. So just some of the things that it's used for. So lenses are in all sorts of things. Obviously glass has been the most obvious one, but cameras, telescopes, microscopes, etc., etc. Lots of things have lenses in them. That's using refraction. In a rainbow, we see the different colours because of the way the light is refracted as it goes through the raindrops, basically act like a prism. And sunsets and sunrises. So when the sun's setting, the light's refracted as it goes through the atmosphere. The density and the angle it's coming in is different, and that basically then results in us seeing more of the red light. The red light's refracted more, so we see that more. Okay, right, last bit that I want you to do for this is there are 2 exam questions. This one has gone a bit fuzzy, sorry, when I've made it big enough to go onto the screen. So these are just 2 past paper questions on refraction, multiple choice ones. So all you need to do for this bit of assignment is just submit the answers to these 2 questions. Okay, I don't need to see your answers to your tutorial questions because you can mark those yourself because you've got the answers. Okay, I'm going to just trust that you have done them. So all you need to actually show me is the answer to these 2 questions, and then I will know that you have done all of it, hopefully. Okay, that's 2 parts done, 1 part to go.